Pick up two magnets right now. Put the north poles together. Feel that? That invisible push in empty air? You want to know why that happens. And I'm going to tell you something that's going to frustrate you. I can't answer that question. Not because I don't understand magnets. I won the Nobel Prize for figuring out the mathematics of electromagnetic forces. I understand them better than almost anyone alive. But your question, the way you're asking it, is broken. And until you understand why it's broken, every answer anyone gives you is going to feel unsatisfying. Here's the problem. When you ask why magnets repel, what you're really asking for is comfort. You want me to say magnets work like rubber bands, or like springs, or like two hands pushing against each other. Something familiar, something you already understand. Then you can relax. You can file magnets away in your mental catalog under things that make sense. But I can't do that, because there is nothing more familiar to compare it to. Magnetic forces are fundamental. They're rock bottom. There's nothing underneath. Let me show you what I mean with a different example. Push your hand down on a table. Go ahead, push hard. Why doesn't your hand go through? You'll say because the table is solid. But that's not an explanation. That's just another word for the thing you're trying to understand. Try again. Why doesn't your hand pass through? Because the atoms are packed together. Better. Keep going. Why don't the atoms in your hand pass through the atoms in the table? Now you're stuck, aren't you? The answer is electromagnetic repulsion. The electrons in your hand and the electrons in the table have the same charge. Like charges repel. When you push down, you're feeling trillions of tiny electromagnetic interactions, all adding up to what you call solid. But here's what's going to bother you. Those electrons never actually touch. There's always a tiny gap between them, a few atomic widths. Your hand never touches the table. Not really. What you're feeling is electromagnetic force acting across empty space. We call it contact because the distance is too small to see. But it's not contact. It's repulsion at a distance. Now, why do like charges repel? You can't answer that. You can say electromagnetic force, but that's just giving it a name. That's circular. That's like saying magnets repel because of magnetic force. You haven't explained anything. The electromagnetic force is one of four fundamental forces in nature. It's not caused by something else. It's not derived from something simpler. It just is. And this is where people get uncomfortable. The force that stops your hand at the table surface, that's the exact same force making those magnets push apart. Not similar, not analogous, identical, the electromagnetic force. So why does one feel obvious and the other feel mysterious? Because you've been pushing on solid objects since you were 6 months old. Your brain built up an enormous library of experiences. By the time you were 2, pushing and grabbing and falling felt normal, natural, obvious. You don't think it needs explaining. But magnets push through visible empty space. You can see the gap. You can slide paper through it. That feels weird. That feels like it needs an explanation. But the weirdness is in your head, not in the physics. When you push on the table, the electrons never touch. They repel at a distance, just a tiny distance. With magnets, the gap is bigger, a centimeter, an inch, big enough to make you uncomfortable. But the force is the same. The mechanism is the same. The only difference is scale. The mystery you feel is not a mystery in the physics. It's a mystery in your psychology. You're comfortable with electromagnetic repulsion at atomic distances because you've experienced it your whole life. You're uncomfortable with electromagnetic repulsion at centimeter distances because it's less familiar. That's it. That's the whole difference. Now you're probably thinking quantum mechanics must explain why the electromagnetic force exists. Wrong. Quantum electrodynamics, the theory I helped develop, is the most precisely tested theory in all of science. We've measured certain predictions to 11 decimal places, and the theory matches exactly. But here's what it does. It tells you how to calculate electromagnetic interactions with absurd precision. It gives you rules, equations, predictive power. What it does not do is tell you why the electromagnetic force exists in some deep philosophical sense. It describes the force beautifully, perfectly, but it doesn't explain it away. It doesn't reduce it to something simpler, because there isn't anything simpler. And that's what I need you to understand before we go any further. The chain of why has to end somewhere. With magnets, with electromagnetic forces, we've hit bedrock. What I can show you is how it works, what patterns it follows, what predictions we can make. But if you're waiting for me to compare it to something more familiar, something that will make you nod and say, oh, now I get it, you're going to be disappointed. Magnets have what we call magnetic dipole moments. little arrows of magnetism, if you want to picture it that way. When you line up billions of these arrows pointing in the same direction, you get a permanent magnet. Those aligned dipoles create a specific magnetic field configuration that stores energy. And here's something you need to know about physical systems. They naturally evolve toward lower energy states. When two north poles face each other, the energy is high. Moving them apart lowers that energy, so they repel. That's as deep as it goes. Now, you want to know why dipoles create fields? I can tell you about moving charges, about electron spin. You want to know why electrons have this property we call spin? I can tell you about quantum mechanics, about the Dirac equation. You want to know why that equation works? Because it follows from combining special relativity with quantum mechanics. You want to know why those theories hold? Because they match what we measure. Because we've tested them millions of times and they work. The chain ends there. But hold on. There's something about magnets that's even stranger than you think. Something that classical physics completely fails to predict. Take a piece of nickel wire, room temperature, bring a magnet near it. The wire gets pulled toward the magnet. Fine. Now heat that wire up. Keep heating it. At about 360 degrees Celsius, something bizarre happens. Suddenly, the wire stops being magnetic. The magnet doesn't attract it anymore. Nothing physical changed about the wire. It didn't melt. It didn't break apart. But the magnetism just vanished. Let it cool back down. The magnetism returns. Heated up again. Gone. What's happening here? Classical physics predicted this shouldn't exist at all. There's an old theorem, the Bohr-van Leeuwen theorem. It proves mathematically that in a classical universe with classical particles obeying classical laws, you cannot have permanent magnetism. Period. Zero net magnetization. The existence of your refrigerator magnets violates classical physics. They shouldn't be possible. So what's really going on? Quantum mechanics. Every electron has this property we call spin, not literal spinning, despite the name. It's an intrinsic quantum property with no classical equivalent. Each electron acts like a tiny magnet. In most materials, these electron magnets point in random directions. They cancel out. No net magnetism. But in iron, nickel, cobalt, something remarkable happens. Groups of atoms band together in regions called domains. Inside each domain, maybe 1 trillion atoms all align their electron spins in the same direction. All the little magnetic arrows pointing together. And when that happens, the tiny magnetic fields don't cancel. They add up. That's a permanent magnet. But why do they align? This is where it gets truly quantum. There's a force between these magnetic moments that's roughly 10,000 times stronger than the direct magnetic interaction between them. 10,000 times. It's called the exchange interaction, and it comes from the Pauli exclusion principle. Two electrons can't occupy the same quantum state. When electron spins align in the same direction, the electrons can get closer together. The electrostatic energy decreases. It's energetically favorable for the spins to line up, not because the magnetic dipoles are pulling on each other directly, though that happens too, but because quantum mechanics and the exclusion principle create this enormous effective force that locks the spins together. That's why heating destroys magnetism. Temperature is atomic motion, vibration, atoms shaking around. At low temperatures, the quantum exchange interaction is strong enough to keep all those spins aligned despite the jostling. But crank up the temperature, and eventually the thermal motion wins. The spins get knocked out of alignment. The domains break apart. The magnetism disappears. Cool it back down. The exchange interaction takes over again. Domains reform. Magnetism returns. None of this makes sense classically. You need quantum mechanics to explain why permanent magnets exist at all. The wave functions, the Pauli principle, the exchange interaction, these aren't optional details. They're the entire story. Without them, you don't have magnetism. And this brings me back to that BBC interview. The interviewer wanted me to explain magnetic repulsion by comparing it to something familiar. But everything familiar is electromagnetic. Springs, rubber bands, the resistance you feel when you push on objects, it's all the same force at different scales. The magnetic force you're asking about is intimately related to electrical forces. They're aspects of the same thing, electromagnetism. If I explain magnetism by comparing it to rubber bands, I'm cheating. Rubber bands work through electrical forces between atoms. I'd be explaining electromagnetism using electromagnetism. Circular, meaningless. So when I refused to give a simple answer, I wasn't being difficult. I was being honest. At the fundamental level, some things just are. Our job as physicists is to describe them accurately. measure them precisely, make predictions, test those predictions, not to reduce everything to something more comfortable. Quantum electrodynamics, QED, the theory I helped develop that describes how light and matter interact. It's the most accurate theory in all of physics. We can calculate the magnetic moment of an electron to 11 decimal places, 11. And when we measure it, it matches. Exactly. Down to the last digit. That's unprecedented precision. No other theory comes close. But here's what QED actually does. It doesn't explain electromagnetism in terms of something simpler. It describes it with mathematical rules so precise you can predict things that haven't been measured yet. And when you finally measure them, the predictions hold. In QED, we talk about electrons exchanging photons, virtual photons. You see these diagrams, Feynman diagrams they call them, showing two electrons approaching each other, a squiggly line between them representing a photon, then the electrons moving apart. People look at that and think, oh, I get it. The force is carried by particles, like throwing a ball back and forth. Wrong. Those diagrams aren't pictures of what's happening. They're calculation tools. Each diagram represents one possible way the electromagnetic field could behave. And to get the actual probability of what will happen, you have to sum over every possible diagram, infinite diagrams. We use mathematical tricks to make that infinite sum give finite answers. And somehow, miraculously, it works. But does that give you intuition? Does that explain why in some comfortable sense? No. It trades intuition for accuracy. You lose the familiar story. You gain predictive power. And that's the choice. You can have comfortable explanations that feel satisfying but aren't actually accurate. Or you can have mathematical descriptions that work perfectly but don't connect to anything you've experienced directly. Physics chose accuracy. Now you might be frustrated. You want to know why the electromagnetic force exists at all. Why does nature have this force? Why these rules and not others? I don't know. Nobody knows. We can describe the electromagnetic force beautifully. We can measure it, calculate it, use it to build every piece of modern technology. But why it exists, that question doesn't have an answer. Not yet, maybe not ever. Some people find that unsatisfying. They want a deeper why. They want to know the purpose, the reason, the ultimate cause. But nature doesn't owe us that. The universe operates according to certain rules. Our job is to figure out what those rules are, not to ask why the universe chose those rules instead of others. Maybe someday we'll find something deeper. Maybe we'll discover that electromagnetism emerges from some more fundamental theory. String theory tries to do that. Other approaches exist. But even if we find that deeper theory, it'll just push the question back one level. Why does that theory hold? Why those equations and not others? Eventually you hit bottom, some set of rules that just are, and we describe them, test them, use them. That's not a failure, that's success. The fact that we can describe nature mathematically, make predictions, test those predictions, and build technology based on them, that's extraordinary. That's what understanding actually means in physics. Not philosophical comfort, not reduction to familiar experience, but accurate description and predictive power. So when you pick up two magnets and feel them push apart, here's what you're feeling. Quantum mechanical exchange interactions between electrons creating aligned magnetic domains. Those domains generating magnetic fields that extend through space. Those fields interacting with the domains in the other magnet. The configuration storing potential energy. The system evolving toward lower energy by pushing the magnets apart. Every piece of that is something we can calculate. We can predict the force at different distances. We can explain why heating destroys magnetism. We can design motors and generators and MRI machines. We can manipulate magnetic fields to trap particles or deflect beams. That's real understanding. That's what physics offers. Not a story that makes you comfortable, not an analogy to something more familiar, but a mathematical framework that describes reality accurately enough to give you power over it. And the reason I couldn't give the BBC interviewer a simple answer is because there isn't one. Not if you want truth. I could have said magnets are like springs or rubber bands. He would have nodded, felt satisfied, and learned nothing, because that comparison is false. Springs and rubber bands are electromagnetic. I'd be explaining electromagnetism using electromagnetism. Instead, I told him the question itself was broken. The kind of why he wanted doesn't exist. And some people saw that as arrogance or evasion, but it was honesty. Sometimes the most truthful answer is that your intuitions about how explanation should work are wrong. And if you want to understand what's really happening, you need to learn a new way of thinking. That's respect. Respect for the truth, respect for the actual structure of reality, and respect for you, for your ability to handle that truth instead of needing comfortable fiction. The electromagnetic force is fundamental. It's one of the four forces that make the universe work. And permanent magnets exist because of quantum mechanics. That's the answer. Pick up those magnets one more time. Feel that push. Now you know what you're actually feeling. Not some mysterious force that needs explaining in terms of something simpler. You're feeling one of the four fundamental forces of the universe doing exactly what it does. Quantum mechanical interactions between aligned electron spins, magnetic fields storing energy, the system evolving toward a lower energy state. That's not mysterious, that's magnificent. And the fact that we can describe it mathematically, measure it to 11 decimal places, predict how it behaves, use it to build motors and generators and computers, that's what understanding actually looks like. Not comfort, not familiar analogies, accurate description and predictive power. So the next time someone asks you why magnets work and you want a simple answer, remember this. The simple answers are lies. The truth is we've hit bedrock. Electromagnetism is fundamental. Quantum mechanics explains why permanent magnets exist at all. And at some point, the chain of why has to end. We describe nature as it is. We test those descriptions against reality. And when they match to 11 decimal places, we've done our job. Not because we've made it comfortable, but because we've made it true.